Hello? Seems that there's some noise, right? Give me 1 second. I'll try to figure it. The reason might be that I don't have a professional mic, but I cannot get one now. So I just start my office hour of the graph theory. I don't know how many students are here, but I just follow my preparation. I'll go through the questions here first and answer your questions if you still have some. So the first question here is about the problem 5 of the problem set 7. Says here. The problem states that a direct graph G is semi-connected for any pair of distinct vertices U and V. Either U is reachable from V or V is reachable from U. So we need an efficient algorithm to determine a graph, whether it is semi-connected or not. So clearly, as he said, we can use the Floyd-Warshall algorithm to solve this problem, but that will be 1 second. we use this algorithm, will be O n cube, where n is the size of B. It is kind of efficient, but it is not efficient enough. So here I'll just give you another algorithm which can solve this problem in time B plus E, or n plus m n equals to B and m equals to E. Oh, I'm sorry for that. Give me 1 second again. So would you mind to set the quality to 720? I mean, I'm not sure about the quality. Yeah, you can change your quality here. It is from like 144 to 720. I think you can set it to 720 and it will become much clearer. Can I solve your problem? Okay. So let's continue to talk about this. So we're not talking about the algorithm which can determine if a graph is semi-connected in B plus E time. Very first, do you guys all know how what the strongly connected component is? Okay. Anyway, I just talk about it. If you know, you just review it, and if you don't know, you can just learn it here. So a strongly connected component of a directed graph is a connected component with this property. This means in this component, any two vertices can reach each other. Meanwhile, here when we define strongly connecting component here, we want it to be maximal. For example, if in a graph like A, B, C, it is a simple link. So for the connected component A, B, since A can reach B, but B cannot reach A, this is not a strongly connected component. So in this graph, the strongly connected components are just the only vertex A, the only vertex B, and the only vertex C, since each vertex can definitely reach itself. So if there is another edge from B back to A, then A and B can together be a strongly connected component, and C is another one. So if there is also another path from C to B, then these three vertices can together form a strongly connected component. Why we need it? Because in a directed any directed graph can be separated into several strongly connected components. And in that case, there won't be any circle in that graph. I mean, if for each such component we treat this as a vertex, then the new graph will have no circle, right? So I think you should be able to understand this. So for example, clearly, this is the strongly connected component of the graph. If this is another one with some vertex inside, if there is a circle, for example, from this one, there is an edge from this component to this component, and there is edge from this component back to this component, then we can just combine these two components together and form a larger strongly connected component in the original graph. But that's a contradiction since we want to make these components all maximal. So in this case, you can consider so for the very first step, find the strongly components of G and G prime using these components as vertices. Well, this can be done in V plus E time. There are several algorithms to do it. I will not go talk too much about this since it's not the main part of this problem, but I can. There is an algorithm called this algorithm can solve this strongly connected components problem in V plus E time using like 2 DFS. You can search for it, and I don't know if you have learned it in class, but if not, you can search for this algorithm. So this is first step, and now we get a new graph, G prime. In this G prime, it is still a directed graph, and there is no circle. Meanwhile, it has at most V vertex and E edges. Oh, by the way, in the new graph, for two vertices like I and J, there is an edge from I to J, if and only if there is in original graph there is an edge from a vertex in the component I to another vertex in the component J. So when we do have this new graph, it is a directed acyclic graph, which means it has no circle. We give the next claim. The claim is like this. I think it should be obvious, right? Since if we can reach U, then in the new graph, clearly we need to add edge from the component of V to component of U. And if in the new graph, there is an edge from the component of V to component of U, then it means there exists some point in the some vertex in the component of V connected, which goes to some point, some vertex in the component of U. And since the component of V, any two pairs, any two vertices in this component are reachable from each other, we can reach this vertex and then go to the vertex, some vertex in the component of U, and then go to U. So this is claim. And another claim is that, so here we use the topological sort. That topological sort for G prime. We can do this because G prime has no cycle. So that we order the such that E J larger than I, there is no pass from J to VI. This is how topological sort works. Still, if you know it, just to review. If you don't know it, you can search for the topological sort, and you will know what it is for. If we have time in the end, I may just talk about it later. So another claim is like this. So let's review the definition of semi-connected. It requires that for every pair of distinct vertices U and V, either U is reachable from V or V is reachable from U. But in the new graph G prime, for any two vertex Vi and Vj, in the where J larger than I, since we have already topological sort, there can't be a pass from J to I, since J is larger than I. So if the graph is semi-connected, then we must have that there is a path from I to J, right? So what does it mean? That means there should be paths from V1 to V2, V3, and let's say Vk, where k is the largest order number. And there should be paths from V2, I'm sorry, to V3, V4, Vk. And finally from Vk minus 1 to Vk. So how can this possible? The only case is that the new graph is like this. This is the only possible case. Actually, you can see that from the first line, we know that there is an edge from V1 to V2, right? And from the second one, there should be an edge from V2 to V3, since they are the most close vertices, and there cannot be any path from V2 to some vertex else that back to V3. It's impossible. So this is the thing we want. Therefore, the problem is like this. In a graph, in a directed graph, with order number of and each vertex is given a number, and we just need to check if there is always an edge from the vi to vi plus 1. And this 1, 2, 3, 4, and 2k, we already have it. Then it can be very simple, and it can be solved in, it can be checked in v plus e time. So we see that the first step, we construct a strongly connected component, and it can be done in OV plus E time. And the second step, we topological solve this, and it can also be done in V plus E time. And finally, we just check if the structure is like this, and it is also V plus E time. So the whole algorithm is V plus E time. So this is how we, I think this should be the most efficient algorithm for this problem. So just ask if you don't understand what I'm talking about, or you have any question about problem 5. You can just type. You guys can just type in the live chat box. I mean, you are not always required to come up with such complex algorithms, but since it is asked by some student, I just tell you what it is like. And by the way, there is a delay of this broadcasting, which is about 10 seconds. So I will answer questions like 10 seconds after you ask it. Anyway, I'll go back to question 5 again if you guys have any problems. So now I just talk about question 6. It is asked by this student here. So the question is, suppose that all the edge weights in a graph are integers in range of 1 to b. How fast can you make Kruskal algorithm run? Or how fast can you make the prim algorithm run? And another case, like it is from 1 to w for some constant w. I don't know why, but I just can't see your question. Well, what I can see is you said that, so to make sure I understand, then just did you see my questions on 5? Nothing else between these two. I'm not quite sure why that happens. Is that exceeding like 200 letters? Is that letters or words? Or if you really have question, you can post that in Piazza, um, and just send me the link. I'll go there and answer the question. Okay. Now let's turn to question 6. Okay, so let's first talk about Kruskal algorithm with this constraint that the weights of the edges are just from 1 to b. So the Kruskal algorithm contains 2 steps. Step 1 is the sort, and step 2 maybe just pick edges. So for step 2, we are always picking like the shortest edge at current time. So what we want is the minimum is how the weight compared to other edges weights. So the real value of the weights actually don't matter. So in that case, the weights of the edge won't affect this part. So this part will always be v log b, right? V log b. So we are just trying to improve the performance of the sorting part. For the sorting part, in most cases, we will use something like quick sort or merge sort, something like that, which will lead to e log e time. Now, since we have that the weights are just from 1 to v, we can use counting sort. So we just store, we can construct a structure maybe named hash. Let's say b equals to n. And each time for each edge of so if the weight of some edge is I, we just insert it edge b has weight I. Then we insert this edge to hash I. right? So in this case, we just use this to represent the quicksort or the merge sort or any sorting method. So to do this, we just need to check each edge and insert it to some to one of the array, and the insert step is just O1. We just need to put it in the end of the array of hash I. So the total time for counting sort is O E. Oh, I'm sorry, it's not OE. We just need one more step. Then we just go from hash 1 to hash n, and for each array we just drag all the edges in this array and put it in a sorted list for each hash. Just by doing this, we can correctly sort all the edges. So here's an example. Suppose the edges are just 2, 3, 1, 1, 7, 2, 4, 5. Then the hash 1 will be okay, and this is edge 1, this is edge 2, edge 3, edge 4, edge 5, edge 6, edge 7, and edge 8. Then we will have 3 and 4, E3, E4 in hash 1. Hash 2, we will have E1, E6. Hash 3, we will have E2. Hash 4, we have E7. And hash 5, we have E8. And hash 6, empty. And hash 7, E5, right? So E1, E2, E3, E4, E5, E6, E7, E8. They are all these 8 edges are in hash 1 to hash 7. Then we go through all these hash arrays in the order of the number, and we just put these edges in order in the list. So we will first go to hash 1 and put E3, E4, and go to hash 2, put E1, E6, and go to hash 3, put E2, E7, E8, and E5. Then this is actually a sorted list. So the total time for counting sort will only be v plus v. Here v is not the number of vertices. It is actually the largest number of weights. But in the very first case, we are given that the weights are just from 1 to v. So since the time is for the counting sort is just O e plus v, the whole algorithm will be e plus v plus v log v. which is this is how we improve the Kruskal algorithm using this fact. And similarly, if it is from like 1 to W, then using this method, we can make it E plus W plus V log V. In this case, since V is definitely smaller than V log V, we can just cancel this V and get the final answer as E plus V log V. But in this case, W is a constant, so we don't know the relationship between W and V or W and E, so we just keep it here. It is not always an improvement. If the W is really large, I mean, if there, since W is a constant, we can say that it is an improvement of the Kruskal algorithm. But in the real case, there might be some limit of the V and E. For example, we be given that the graph will have at most, for example, 1,000 edges. But if W is more than 1,000 log 1,000, which is E log E, then we will still use the original algorithm instead of this one, since that will cause worse result. So this is all for the Kruskal algorithm. Then we go to the prims. For prim algorithm, so it is generally adding new vertices into the vertex set, and for each time, we just pick the vertex which is closest to the current vertex set. I think you should be able to, you should understand this, right? It is just a prims algorithm. Now we are given that the weights of the vertices are just from 1 to B. So what can we do to make it faster? We still construct the lists L1 to Ln. The very first is all lists are set empty, and these lists will be used to represent the priority queue or the heap during the algorithm. So suppose each time you extend your vertex set to a new vertex, say U. So in some step I, we add U to the vertex set. Then in the original algorithm, you need to put all edges. You need to put all edges UV into the priority queue or the heap. But in this algorithm, we just put each UV with weight, we say W into the list LW. You know that if we put a match into the priority queue or the heap, it will be log V time. This will be log B. But in this case, it will be O1. We just need to add it to the end of the array of LW. And for each time we want to pick the current shortest, the vertex which is currently closest to the current vertex set, we just check. This is how we do in the original algorithm to get this vertex we want, which will also be log B. Now check from L1 to Ln and pick the first get. What does it mean? It means that if the L1 is not empty, then we just pick some pick one vertex from pick the edge from L1, and we know which vertex we need to add to the vertex set. Yeah. So for this one, it can be OB. Well, give me 1 second. Yes. The total time of this will be OB, and we will add n vertices to the vertex set. So the total time for adding vertices is B squared. Total time for adding and deleting edges to or from the lists of the OE. Since for each edge we will add it to the list at most once, and we will just delete it from the list at most once. Like we said, for each time we add it, we just need to put it to the end of the array, and it is O1. But each time we need to delete it, we can set a cursor which represents the start of the list. So just need to move this cursor one step forward. So that is also O1. So the total time of adding and deleting edges is OE. So the total time of the algorithm is B squared plus E. This is how I improve the Prim's algorithm. In most cases, this will be better than the original algorithm, since B square is at most in most cases B square is actually the same as E. I mean the size of them. But since I myself don't have the solution to this problem set, I'm not quite sure if this is the best performance or if we can have other better ways to improve it. But till now, this is what I can think of. If the constant if it is from 1 to a constant w, we just need to change it to v times w plus e. Actually, it's the same as problem 9, as I see. Oh, by the way, it can be improved by using priority queue or heap for these lists. I will talk about that later in question 9. So here, these are all for question 6. Question 6 and question 7 are actually related, so I just finished talking about question 7 here. So the question 7 asks that suppose the weights are randomly chosen real numbers from the uniform distribution over the interval from 0 to 1, which algorithm will run faster? So question 7 is different from question 6. Since the weights of the graph are real numbers between 0 and 1. Actually, there are infinitely many real numbers in this interval. Thus, we cannot use the same methods here. We cannot construct infinitely many lists or arrays to help improve the sort or the adding and deleting operations. But here we have another sort called bucket sort. Sorry. It will be really good, really efficient for the case that all the values are randomly chosen from the uniform distribution over some interval. It will take some time to talk about this sorting, but here's the link. You can actually find it in Wikipedia. I'll just tell you that in the case that the weights are randomly chosen from the uniform distribution over 0 to 1, the bucket sort will reach its average performance, which is On plus K. Actually, the On plus K here means On, which means it will be OE in Kruskal's algorithm. And meanwhile, the Prim's algorithm will not be improved with this fact. Thus, clearly, the Kruskal's algorithm will be better. So this question is actually simple. You just need to know that there is such a sort method which can improve Kruskal's algorithm in this way, and the Prim's algorithm cannot be better. Then you will get the final result, which is the Kruskal's algorithm will be better. So before I go to question 9, you guys can just ask any question here. I know it is when I talk about question 6, it is maybe a little bit confusing since I talk too much. You can ask if you don't understand. Okay, seems that everything is good. Now let's go to question 9. It says that the weights of the edges are from 0 to w for some constant w, and we need to modify the extra algorithm to make it O w times b plus e. So you guys should know that the Prim's algorithm and the Dijkstra's algorithm are really similar in the structure. They are always keeping a set of vertices and always picking another vertex which is closest to the current set to update the whole problem. So here, similar to question 6, we construct L0, L1 to LW, initially empty. So similar to question 6, O WB for adding vertices. Deleting edges. Yeah, so using the same method as the Prim's algorithm in question 6, we can make the Dijkstra's algorithm here to become W times B plus E. Since, as we know, for each vertex we need to add, we just need to search all the lists. The worst case is that the edge we want is in LW. That means we need to search all W plus 1 edges with that is OW. So for all vertices, it will be W times B, and for each edge, it can be it will only be added to the list once and will be extracted only once, at most once. I mean, so that will be OE in total. But for the second part of this problem, we want to make it O E plus E of W. So how can we do this? Use heap. This. This is the main part we use to make the algorithm in this time. So it is like this. Each time when adding a edge of weight k to LK, we check if LK is empty before adding this edge. If so, that means this is the very first edge in LK. If yes, we put K into the heap. order priority queue. We should all know that. So in this way, every time when we try to extract an edge, we just need to check the heap, and it will. This will be O log W. Since the heap will contains at most W plus 1 elements, which is 0, 1, 2, and 2W. When we want to extract edge, okay, get the smallest value K from the heap. That means that when the minimum value in the heap is the minimum K, which LK is not empty. Since the heap will always contain all the lists that are not empty. Since LK is not empty and this is the minimum list which is not empty, we will just pick one edge from this list. So to get this K, it is O1. And when we an edge from LK, we check if LK is empty after removing this edge. So this case is that the list contains only one edge, and since it is not empty, it is in the heap. But this time we remove this edge. Actually, what I mean is we have used this edge, so the list becomes empty. So we need to remove this K from the heap. This is also log W. In this way, we see that for each for the edge part, it will become E log W instead of OE before. But for adding the vertex, we do not need to search all W lists, but just get the list we want from the heap. Give me 1 second. Oh yes. So for adding the vertex, for each time it takes O1 to get edge or vertex. O log W to removing the list from the heap. So total. So the whole algorithm will be E log W plus V log W, which is V plus E log W. Okay. That's all for question 9. So we have talked about question 5, 6, 7, and 9. ask questions if you have. Chapter 20, I'm not quite sure. Ask the professor. If you want, I can ask the professor and post that on Piazza. If okay, that's all for today's office hour. Happy weekend. Oh, you mean the time for the new chapters? I really don't know, since that's I'm not responsible for that. I'm sorry. I'll ask a professor, and if I can get an answer, I will post that on Piazza and let all of you know. Okay. Thank you for watching. Happy weekend.